You ever stop and think about like all the gadgets we use every day? Like from our phones to the lights to, I don't know, just everything.
Yeah, yeah, absolutely.
At the end of the day, it's all about electricity and circuits.
Exactly.
I feel like understanding circuits can sound a little bit intimidating, but it's actually really useful and I think kind of mind-blowing.
It is.
So think of this as your personal guide into the world of circuits and electricity.
Absolutely. And today, we're specifically diving into the fascinating world of DC circuits. That's direct current circuits, not just the basic series and parallel ones.
Right, right.
We're going to go deeper and look at more complex networks.
We're going to figure out those voltages and currents within those networks.
Exactly.
And we have a great resource to guide us through this. We have a really comprehensive summary of a whole chapter dedicated to DC circuits.
Yes, we do.
And it covers everything. I mean, from resistors in series and parallel to Kirchhoff's rules, which we'll get to electrical measuring instruments, and even RC circuits and power distribution systems.
Yeah, we're covering all the bases here. We're going to go from the fundamentals to really practical applications in our everyday lives.
By the time we're done here, you should have a pretty good grasp on the main principles of DC circuits.
We aim for those light bulb moments where those abstract concepts suddenly just click.
Yeah, those aha moments, those are the best.
Exactly.
Okay, let's start with something pretty fundamental. Resistors.
Okay.
Resistors in series and in parallel. So imagine you're driving down a single-lane road where everyone has to follow the car in front of them.
Okay. Yeah.
That's kind of like a series circuit, right? Everyone's in a line, and if one car stops, everything behind it comes to a halt.
A perfect analogy. In a series circuit, resistors are connected one after the other, forming a single pathway for the current. And the same current flows through each of those resistors.
It's like the flow of traffic, right?
Exactly.
Now, the voltage across each resistor, that's like the electrical pressure that gets divided.
Yeah.
So it's like each car in the line sharing the burden of the journey. And the total resistance in that single lane road.
You just add up the resistances of each individual car, or in
What?
this case, each resistor.
There's a formula for that. It's pretty simple. War and weak, R1 plus R2 plus R3 plus $1 and so on, right?
Yes.
So the more resistors you add in series, the higher the total resistance becomes.
Precisely. More obstacles in the path.
It makes sense, right? You're adding more and more obstacles. So if you think about a simple lighting system with multiple bulbs, understanding this series resistance is key. You have to make sure that the power source can handle the total resistance so all the bulbs light up properly.
Absolutely. If you don't consider the series resistance, you could end up with some dim bulbs or even overload the circuit.
Right, exactly. Now let's change our analogy a bit. Let's imagine a multi-lane highway with multiple paths to get from point A to point B. This is more like a parallel connection in a circuit.
Perfect. In a parallel circuit, each resistor provides a separate pathway between 2 points.
More lanes means smoother traffic flow.
Exactly. And in this circuit, it means more current can flow without increasing the voltage.
So the voltage, that electrical pressure we talked about, is the same across each of the parallel resistors.
Yes, just like each lane on that highway shares the same entry and exit points.
But the current gets divided among the different lanes, or in our case, the different resistors.
And the current through each resistor depends on its resistance. Lower resistance means more current flows through that path.
Right, it's like the wider, less congested lanes on the highway naturally attracting more cars.
Absolutely. Now, calculating the total resistance in parallel is a little bit different. It involves reciprocals.
Yeah, the formula looks a bit intimidating. Frac 1 R1 plus Frac 1 R2 plus Frac 1 R3 plus direct.
But there's a simpler one for just 2 resistors in parallel. Rokuron Frac 1 plus Rokuron.
And remember, the key takeaway is that adding more resistors in parallel actually decreases the total resistance because you're creating more pathways for the current to flow.
It's like adding more lanes to that highway.
Right. Now, of course, real-world circuits aren't always so simple, are they? It's not always just purely series or purely parallel.
Not at all. Most circuits you'll find are a combination of series and parallel connections, forming more complex networks.
But the good news is that often we can simplify those networks to make them easier to analyze.
Yes, you can often break them down step by step until you get to a single equivalent resistance for the entire circuit.
And that's where things can get a little trickier, right? When those simple series and parallel rules aren't enough, that's where we turn to Kirchhoff's rules.
Precisely. Kirchhoff's rules are our tools for analyzing those more complex circuits. They're based on fundamental physical laws.
It sounds a bit formal, but they're actually really powerful.
They are. Before we jump into the rules themselves, there are a couple of key terms we need to define: junctions and loops.
Okay, let's hear them.
So, A junction is any point in the circuit where three or more wires connect. It's like an intersection where currents can split or merge.
Makes sense. So multiple paths converging or diverging?
Exactly. And a loop is any closed conducting path within the circuit. It's like a circular route that the current can follow.
Okay, got it. A complete circuit.
Right. Now, the first rule, Kirchhoff's junction rule, is all about the conservation of electric charge. It says that the total current flowing into a junction has to equal the total current flowing out.
So what goes in must come out.
Exactly. No electricity just disappears or magically appears at a junction. The charges have to keep flowing.
So like water flowing through pipes.
Exactly. It's like plumbing. The water flowing into a junction has to equal the water flowing out.
And mathematically, this is represented as the sum of all currents at a junction being zero.
Yes, we use the symbol sig on I or equals L to express that.
So the direction of the current matters here, right?
Absolutely. By convention, currents flowing into a junction are considered positive, and currents flowing out are considered negative.
It's a bit like accounting. You got to keep your debits and credits straight.
Exactly. As long as you're consistent with your signs, the math will work out. So for example, if 2 amps are flowing into a junction and 1 amp is flowing in from another branch, then 3 amps must be flowing out through the third.
Okay, that makes sense. Now what about the second rule, the loop rule?
The loop rule is all about the conservation of energy. It states that the sum of all voltage changes around any closed loop in a circuit must be zero.
So it's like taking a round trip. No matter what route you take, you end up back where you started.
Yeah, that's a good way to think about it. As you go around a loop, you'll encounter voltage sources like batteries, which increase the voltage, and components like resistors, which cause a voltage drop.
Right, gains and losses have to balance out.
Exactly. And when you sum up all these changes, accounting for their lines, you always get zero when you complete the loop.
And again, the signs are super important here too, right?
Absolutely. We need to be consistent. For example, if you're moving through a resistor in the same direction as the current flow, there's a voltage drop, which is considered negative. If you move against the current, it's a voltage rise, considered positive.
So it's all about carefully tracking those potential changes as you go around the loop.
Yes, and once you have a good grasp of these sign conventions, applying Kirchhoff's rules becomes much easier. You can set up equations for each junction and each independent loop in the circuit.
And then you can solve those equations to figure out the unknown currents and voltages.
Exactly. Kirchhoff's rules are like giving us a set of rules for a puzzle. And by solving that puzzle, we can unlock the secrets of how the circuit behaves.
Okay, so we've talked about the theory of circuits, but how do we actually measure those currents and voltages in real life?
Well, most common electrical measuring instruments, like ammeters for current and voltmeters for voltage, are based on a device called a D'Arsonval galvanometer.
And that sounds pretty complicated.
It might sound that way, but it's a really neat little device. It's essentially a coil of wire suspended in a magnetic field. When current flows through the coil, it interacts with the magnetic field and causes the coil to rotate.
Okay, so it's like a tiny motor?
Sort of. The rotation of the coil is proportional to the amount of current flowing through it. And this rotation moves a needle or pointer that indicates the current on a scale.
So a small current causes a small rotation, a large current causes a large rotation.
Exactly. The galvanometer is really sensitive, but it has limitations. It can only handle a small amount of current without being damaged.
So how do we use it to measure larger currents? That's where the ammeter comes in, right?
Yes. To make an ammeter, we connect a very low resistance resistor called a shunt resistor in parallel with the galvanometer.
So it's like creating a detour for most of the current.
Precisely. Most of the current flows through the shunt resistor, and only a tiny safe fraction flows through the galvanometer.
And because they're connected in parallel, they have the same voltage across them, right?
Exactly. And we can use that fact to calculate the exact value of the shunt resistance needed to get the desired range for our ammeter.
And ideally, you want the ammeter to have very low resistance overall, so it doesn't interfere with the circuit we're measuring.
That's right. An ideal ammeter should have zero resistance. But in reality, that's not quite possible.
Yeah.
But we get pretty close.
Okay, what about measuring voltage? That's where the voltmeter comes in.
For a voltmeter, we connect a high resistance resistor, called a series resistor, in series with the galvanometer.
So this time, we want to limit the current flowing through the galvanometer.
Exactly. We don't want the voltmeter to draw a lot of current from the circuit because that would change the voltage we're trying to measure.
So it's kind of the opposite of what we did for the ammeter.
Yes, exactly. And just like with the ammeter, we can carefully choose the value of the series resistor to get the desired voltage range for our voltmeter.
And again, ideally, you want the voltmeter to have very high resistance so it doesn't affect the circuit too much.
Precisely. An ideal voltmeter has infinite resistance.
Okay, so we've got ammeters for current, voltmeters for voltage. There's also the ohmmeter, right?
Yes, the ohmmeter is specifically for measuring resistance. It basically applies a known voltage across the resistor we want to measure and then sees how much current flows through it.
Using Ohm's law, 3Fs of UI, we can then calculate the resistance.
Exactly. It's a very handy tool.
Now, there's one more instrument mentioned in our summary that we need to talk about, the potentiometer.
The potentiometer is a bit more specialized. It's used to measure the electromotive force, or EMF, of a source without drawing any current from it.
So it's measuring the potential of a source without actually using any of its power.
That's right. It's a very precise measurement technique.
How does it work?
Well, it uses a long wire with a known stable current flowing through it. This creates a voltage gradient along the wire.
Okay.
Then we use a sliding contact to tap off a portion of that voltage.
So you can adjust the voltage being tapped off.
Yes, precisely. And then we compare that voltage to the unknown EMF using a very sensitive detector called a galvanometer.
So we adjust the sliding contact until the galvanometer shows zero current flow.
Exactly. That means the tapped off voltage is exactly equal to the unknown EMF.
Clever. And because no current is flowing from the source at that point, we're getting a really accurate measurement of its EMS.
That's right. Now, we can also use ammeters and voltmeters together to indirectly measure resistance and power in a circuit.
But we have to be aware of their own internal resistances, right?
Absolutely. Their internal resistances can slightly affect the measurements, so we need to take that into account for accurate results.
Okay, so we've covered the basics of resistors and how to measure electrical quantities. Now let's dive into something a little more dynamic, RC circuits.
RC circuits, which combine resistors and capacitors, introduce a time element into our circuits.
So things aren't just happening instantaneously anymore.
Exactly. The behavior of an RC circuit changes over time as the capacitor charges or discharges.
Okay, let's start with charging. Imagine we have an uncharged capacitor and we connect it in series with a resistor and a battery. What happens?
When you close the circuit, current starts to flow from the battery. The capacitor, initially having no charge, acts almost like a short circuit.
So a lot of current flows at first.
Yes, because there's very little resistance. But as the current flows, charge starts to build up on the capacitor's plates.
Okay.
And this buildup of charge creates a voltage across the capacitor, which opposes the battery's voltage.
So as the capacitor charges, the current flowing through the circuit decreases.
Exactly. It decreases exponentially. Eventually, the capacitor becomes fully charged, and the current drops to zero.
At that point, the voltage across the capacitor equals the battery's voltage.
Yes. Now, this charging process doesn't happen instantly. It takes time, and that time is determined by the time constant of the RC circuit.
The time constant is just the product of the resistance and the capacitance. Tau equals RC tau.
Right. A larger time constant means a slower charging process.
And after one time constant, the capacitor is about 63% charged.
Yes, and after about 5 time constants, it's considered fully charged.
Okay, so that's charging. What about discharging? Let's disconnect the battery and connect the charged capacitor directly across the resistor.
In that case, the capacitor starts to discharge through the resistor. The stored charge flows out, creating a current in the opposite direction to the charging current.
And as the capacitor discharges, the voltage across it decreases.
Yes, and so does the current. Both decrease exponentially.
And that same time constant tau, RC no, governs the discharge rate as well.
Precisely. After one time constant, the capacitor is discharged to about 37% of its initial charge.
But after about 5 time constants, it's pretty much fully discharged.
Right. It's also important to think about the energy flow here.
During charging, the battery supplies energy, some of which is stored in the capacitor, and some is lost as heat in the resistor.
Yes, and during discharging, the stored energy in the capacitor is released and dissipated as heat in the resistor.
Okay, so RC circuits bring this interesting time-dependent behavior to DC circuits. Now, let's talk about how these principles apply to real-world power distribution, like in our homes and cars.
In both cases, the key principle is the use of parallel connections.
We talked about parallel resistors before, but why are parallel connections so important for power distribution?
Imagine if all the electrical outlets in your home were wired in series. If one device failed, everything would stop working.
That would be a nightmare.
It would. But with parallel connections, each device has its own independent path back to the power source.
So if one device fails, it doesn't affect anything else.
Exactly. Each device gets the full voltage, and they can all operate independently.
That makes so much sense. So in our homes, we have a line with a neutral wire and a hot wire, right?
Yes, the neutral wire is grounded, and the hot wire carries the voltage. Outlets and lights are connected in parallel across these wires.
And we have fuses and circuit breakers for safety.
Absolutely. They protect against overcurrents, which can happen if there's a short circuit.
A short circuit is when the hot and neutral wires touch, right?
Yes, creating a path of very low resistance, leading to a huge surge in current. Fuses and circuit breakers interrupt the flow of current in such cases, preventing fires.
And those outlets with the test and reset buttons, those are GFCIs, right?
Yes, ground fault circuit interrupters. They're particularly important in areas where water is present, like bathrooms and kitchens.
They protect us from electric shocks.
Exactly. They detect imbalances in current flow, which could indicate that some current is flowing through a person or a faulty appliance. And they trip very quickly, interrupt the current.
So those are really important safety features. Now, what about cars?
Cars use DC systems, typically around 13 volts, supplied by the battery and the alternator.
And again, everything is connected in parallel.
Yes, just like in homes. But in cars, the metal body of the vehicle often serves as the ground connection.
So each device only needs a positive wire running to it.
Exactly. And just like in homes, cars also use fuses or circuit breakers for protection.
So whether it's our homes or our cars, parallel connections are essential for safe and reliable power distribution.
Absolutely. They allow for independent device operation, and safety features like fuses and circuit breakers protect us from dangerous situations.
Okay, let's quickly recap what we've covered in this deep dive into DC circuits. We started with the fundamentals of series and parallel resistors, understanding how their combined resistance affects current flow.
We then move on to Kirchhoff's rules, which allow us to analyze more complex circuits by examining junctions and loops.
We learned about galvanometers, the heart of ammeters and voltmeters, and how those instruments are designed to measure current and voltage without significantly affecting the circuit.
We explored RC circuits, which introduce a time element into our analysis, with capacitors charging and discharging at rates determined by the time constant.
And finally, we discussed the importance of parallel connections and safety features in power distribution systems, both in our homes and in our vehicles.
And through all this, we've gained a solid understanding of how direct current circuits function, from simple combinations to complex networks and practical applications.
And it's really amazing to think about how much our world relies on these fundamental principles of electricity.
It is. And as our technology continues to advance, our understanding of circuits will become even more important.
So as we wrap up this deep dive, I'm left wondering, what future innovations will be made possible by an even deeper understanding of these principles?
That's a great question to ponder. Will it be in energy storage, or maybe even more powerful and efficient electronics?
The possibilities are pretty exciting.
They are. And with that, we've covered all the key points, theories, findings, and examples from the chapter summary on direct current circuits. We've really delved into the heart of how electricity works in our world.
And I think we've given our listeners a lot to think about.
I hope so. Understanding DC circuits is a fundamental step in appreciating the technology that surrounds us.
So keep those aha moments coming.
And always keep exploring the fascinating world of electricity.